Hello, my name is Qubix and welcome all to the second seminar on Revision 2025. In this seminar I will give a talk about how to build a 3D geometry engine from scratch. So what are we actually talking about here? And a 3D geometry engine on an 8-bit CPU, is that really a good idea? Is that possible? And we will see that, yeah, it's entirely possible. And of course, at first we have to think about what basic geometry transforms you would need. And then we will go about prototyping such an engine in a higher level language. And we will see, well, higher level language means actually basic here on the 8-bit CPU. And we will see it's not fast enough for this. And to get to a good result, we need to do a transition to machine code. And we will employ fixed point arithmetics for this and fast line routines. And that being done, we can do iterative improvements to improve the visual result that amounts to double buffering, to hidden lines, and to frame syncing. And I will also give an outlook what is necessary to advance beyond the showcase demo at the beginning. And that would be filled vectors, lighting models, texture mapping, and hardware support. So what is a 3D geometry engine? Well, the visualization of animated 3D scenarios is one of the key disciplines in the Demoscene. You have seen it in the intro. The later parts of the intro also take a scene, and it takes the artist's imagination of a virtual world into the real world, and that is also what we then have seen on the screen. And what is da? Ist alles da? Sorry. For such an engine to work, we process geometric data, and they are then drawn on screen by graphics instructions, graphics primitives, lines, points. And the idea for a 3D geometry engine is that we want to abstract the processing step from the data input and the graphics output, so we can reuse the same engine for different hardware, for example. And on today's computers, it's the graphics cards and the graphics LPAs that do the hard work, but you can also do it on extremely, or say, a fairly old hardware like the VIC-20, which is from 1980, and do something like this. We have here an 8 megahertz 8-bit CPU and a bitmap resolution of 69 times 160 pixels. And yet, this is a wireframe animation of a cube. And inside, there is an icosaeder, and it's being updated 10 times per second. And it uses a double buffering, and the whole thing can also be adapted to different render methods. So what are we actually seeing here? That's not quite obvious. We have this construction here. And now, instead of being the leftmost big dot on the optical axis, we are viewing the whole setup from the outside. What you see there is an optical axis. you see the projection plane on the left side, and you see a simplified object on the right side. And the idea is that it doesn't make any difference if you are seeing the object point itself or a projection of it on the projection plane. And this basic principle is the intersect theorem. And to make a little bit of background about that, I got interested in that topic about 1992 when I got an Econ Archimedes, and it was for the first time possible to write such graphics routines in interpreted BASIC. Before that, you had to use Macking code, and at that time, I saw for myself it was possible to get some knowledge about that and program that stuff myself. And if you do such geometry processing, you have a collection of formulas you will use, and that's about the only slide in that whole talk, seminar, that contains mathematic formulas. But you see that those are not that many. You will be scaling things, that means stretching them or making them smaller. You will translate them, putting objects into another place. You rotate them, that means rotate them around. You will also need mirroring, and to get the central perspective, you will also do the projection process. And one word I should tell about the coordinate versus the vector matrix notation. The rest of the seminar will concentrate on the coordinate notation, because you can write everything quite easy and quite smallish with the vector matrix notation, but then it's only small on the screen, but it's not small in the program. Then you have anyhow to program it out. So what is then scaling about? And there is something like uniform scaling and non-uniform scaling. You can apply uniform scaling to objects, and then they will just become bigger. But if you take the scaling on the whole scene, including the projection plane, the result does not change at all. If everything in our world would become a factor 2 bigger, you wouldn't notice it. There is something other to be said about non-uniform scaling. The screen pixels we have on the display devices are not necessarily square. And there are some good examples. For example, the Hercules graphics card that has pixels that are only about 2/3 wide as they are tall, and they are clearly non-square. Also, the NTSC C64 has non-square pixels, and on the VIC-20, they are also non-square. They are more wide than they are tall. And if you ignore that, you can't do good graphics. Especially, you can't do good vector graphics, because the view is distorted, and when you rotate objects, their angle change. So, and you need the scale operation to compensate for any non-square pixel aspect ratio. Yeah, translation is maybe the easiest one. You define a point in the room, in the space, which is the anchor of all geometry operations. So, and those translations you can also concatenate, and all the other geometry transforms are being set with respect to the origin. And if you do any of those transforms on a known origin point, you have to do 2 translations. And that's actually also the definition of a vector. A vector is a translation in space, and not that thing that looks like an arrow. That's only something that represents a vector. Yeah, what you also will need is a rotation. We will be going to rotate things in 3-dimensional space, but you can also, to start out, you can also do that in a plane, of course. And to characterize rotation in the plane, you only need 1 rotation angle. If you do it in 3 dimensions, you need 3 rotation angles, or 1 axis and an angle. And it's always important to remember, if you do rotations in 3D and exchange them, the result is different. When I got about to define that example that I showed you at the beginning, I had to think about what is the possible extent of the object shown on screen. And here is a construction that aimed to determine the necessary scaling factor. And if you take the cube, the edges, the corners are at most the square root of 3 from the origin, and they trace out a sphere with that radius. And if you put the center of the cube at the distance given in the diagram, you see that at maximum the projection is about 1/2 of a unit. And that defines us a good scaling factor. What we would also need for the terms of projection is that we clip the objects against the possible viewpoints. So if it's outside the so-called frustum or straddles it, then you need to clip things. And I put the object so into the screen that it is not necessary to clip or do any culling. What we will also need is mirroring, and this comes around with the handedness of coordinate systems. So in the 3D world, we usually use a so-called right-handed coordinate system. If we turn the x-axis into the y-axis, the z-axis points along the thumb. And positive angles, they turn counterclockwise. And for some reason, display coordinates are left-handed. So it's exactly the other way around. And we also have then that angles turn clockwise. So one notable exception of this is the video display unit of the BBC Acorn. They actually also use the right-handed coordinate system with the origin in the bottom left corner. Otherwise, we will need to mirror coordinates at some place. So, and with this, with all those formulas, it is really possible to do a first prototype in BASIC. And I use an own a basic extension for that, to have a minimal set of graphic instructions. In principle, all you need is a fairly fast line routine for this, and you get one animation phase every 2 seconds. That's not really, it's more like a thumb cinema. Really, it works, but it is slow. We have an interpreted language, and we have a CPU with no built-in floating point. And what we need to do is transition to fixed point arithmetic, but first we need to think about what precision do we need, what range of numbers do we need, are the rounding errors that we need to consider, and what about overflows? Yeah, and the basic idea is to rescale the number range. So the native integer range of the CPU, in this case 8-bit, is that what we need to keep all the coordinates that exist. And I said earlier that the cube coordinates are at most at the square root of 3. The square root of 3 is 1.7 about, so we are just in that range between -2 and +2. And if we have set up that system, the additions and subtractions are elementary operations of the CPU. They are exactly as fast as integer operations then. Yet we are calculating with something that is like a float number for our purpose. What is not so simple is the multiplication. On this CPU, we have to use the difference of squares method. That is about 1/10 of the speed of addition and subtraction. So if we take into account that the 6502 has to fetch the data, has to add, and then to store, that takes about, say, 8 cycles, and the multiplication is about 60 cycles, not quite a factor 10. And the division is even more expensive, and but if you take a sharp look at formulas, you can re-express them, so you can do the division by a multiplication with reciprocals. And when I had laid out all those ideas, the first step for me was to do a proof of concept. I used the integer variables of the basic interpreter, not for their speed, because they're actually slower on the CBM, on the Commodore, than the float variables, because there are extra conversions involved. But I wanted to make sure that even if I make all the calculation with integer numbers, everything still works. And the next thing was I first had the transforms rather in that point using lots of variables, and then I streamlined the transforms to minimize temporaries. And then, as a third step, I took a C program to emit the assembler, the full source code for the assembler. That had 3 reasons. First, I wanted to see how much code comes out of this, and the assembler I use actually has not good macro support at all, and in my opinion, macros are also a two-sided sword. They easily hide optimization possibilities. And the result, and I was still using BASIC for the graphics, was 2 frames per second. So actually, all the geometry calculations were so fast that they were no longer the bottleneck. And that led me to the next step. The line routine built into the basic extension only does about 4,000 pixels per second. Inside for basic itself, that's quite fast enough. That speed would be wasted. Any more speed would be wasted because normally from the view of the other parts of the program, even 4,000 pixels per second are fast enough. I changed the line routine to one with that is able to do about 20 kilopixels per second on 1 megahertz CPU. And for this I adapted an example from Codebase 64, but that one needed 2 main loops. I could reduce it to 1 main loop. I also optimized other things, and then the result was 12 frames per second. And the only thing remaining in BASIC then was the update of the angles. So in principle, that program can be still adapted to not only do a free rolling rotation, what I usually do, and for one thing, it was not fast, but rather flickery, because 12 times per second the screen is cleared, and then you see the redraw of the next animation phase, and that looks like an oscilloscope and could be improved. And then sometimes you look around and see suggested and what kind of methods could be used to improve things. And one of them is the so-called XOR method. And you undraw the lines by painting over them. The XOR method inverts lines instead of just setting them. And actually, the flicker can be reduced by that method by a good amount, and even the frame rate is comparable. Of course, you have to consider there is a break even when you always have to draw the object twice then. And when the clearing of the screen is faster than drawing once, you are at a break-even point. But in my opinion, the visual result is questionable, because if you look at the animation, the edges during update do not anymore match up. That's quite visible during rotations, but also under translation, and it often looks as if the objects are falling apart. That's okay if you don't mind the visual result, and otherwise it's really only okay if there's no room for a second bitmap. You can improve if you use a shadow buffer. And the goal is we want to minimize the apparent screen update time, and for this we simply draw anything, we draw the animation, the new animation phase on a hidden bitmap, and that may take some time, and that being done, we copy over the shadow buffer into the display bitmap. That can be done in different ways. I'm favoring the method going against the grain, because then you have only guaranteed one transition point, but the result anyhow, I needed to stop in a certain animation phase to get that picture. You see tearing artifacts. And that's not the end. We can improve on that further. And this is using page flipping. And here's the goal: not only minimizing the apparent screen update time, but nullifying it. and this requires that the video chip is able to display at least 2 different bitmaps. We also don't anymore have to copy the bitmap itself, and of course that makes everything faster. On the VIC-20, it is not possible to make a double buffering for the whole graphics screen. I had to reduce the screen size for that, but I made sure beforehand that the whole animation already was only that big as it would be later in the page flipping version. There is one caveat, and I address this on this next slide. If there is a different CPU load, you might notice an uneven frame rate that's less apparent when you only have, say, 10 frames per second. But if you get in the region of the update rate of the display itself, it becomes quite apparent. If an object is updated every two thousandths during one time, and every three thousandths on other times, and if that changes randomly, that can be quite unnervous, and it's also called jada. And as an example, I take the hidden lines algorithm, and mind you, this is still all using the same geometry engine, and I'm just changing the display method. I add a visibility check of surfaces, and from that I go to the visibility check of the edges. And the idea is that at least one of the 2 faces of the cube needs to be visible, and then the edge is also visible. In that simplicity, that only works for convex objects. It becomes a little bit more complicated if you have non-convex objects. Because of the notion of the signed area, we also have to take the coordinate handedness into account. What I did was actually constructing this cube on paper, and if you go about this, you see the signed area is defined as that you take 3 points, and they are also form a right-handed arrangement, and then the area is positive. And then when the face looks away from you, 2 of the points change their position, and the area then becomes negative, and then you can't see that surface anymore. In any case, depending on how the cube is being shown on screen, you only see either 4 lines, 7 lines, or 9 lines, and that gives a very uneven CPU load. And this calls for a frame rate limiter. And this example, for example, switches between 25 and 17 frames per second on a PAL VIC-20, and that is very noticeable. And for this reason, I introduced the frame rate limiter. So it's now only 17 frames per second. In the end, and this is for the example of the at the beginning, the icosahedron inscribed in the cube. I also improved on the line routine. The line routine I use does about 30K pixels per second on the VIC-20, and it's 50% faster than the other example on Codebase, but still about the same size. And it's also quite comfortable because it comes with an integrated change of the draw operation between set, reset, and invert. So it can be used as building blocks, as building block for many other programs. And as said, I used this in the showcase demo. Now, thank you. Okay, it's nearly complete. That's just 60 moves. Not too far. 60 moves to put it back. Okay. When we have that idea to draw the cube, what would we like to do with it else? So you see there is a wireframe cube that is possibly the simplest method, there is also not simpler. You can also do plot a dot cloud. Then you only have a bunch of dots that you move around. The next then is the wireframe model. Then you would do hidden lines, but there is also you can fill the surfaces. You can do flat shading. You can apply lighting models. You can do nowadays it's much more easier perspective correct texture mapping, and as said, pour all that into hardware. So when we want to do filled vectors and flat shading, what do we need? We can actually do this with the standard Bresenham algorithm, and we don't usually plot the whole line anymore, but rather only delineate the endpoints either horizontally around the polygon or vertically, and then use specialized routines to draw vertical and horizontal lines. What we can do with 1 bit per pixel bitmaps is parallel processing. Those are the so-called AO fillers. And we can even use the hardware for this. On the C64, for example, sprite fillers are possible, and these are prominently shown, for example, in the snapshot demo. And on the Amiga, there's of course the blitter inside that has a fill mode dedicated to this. And what's possibly not that quite widely known is that you can also misuse the ham mode to do fills. The ham mode is the built-in hold and modify mode, a graphics mode of the Amiga, and it automatically propagates the colors to the right, and you only need to set a pixel in one color in ham mode, and then you don't have to do anything anymore. The color is just being propagated to the right, and it ends when it encounters another pixel, which then switches the color again, and this is a hardware fill. We would also like to include the lighting in a scene, and then you usually can't avoid vector mathematics, linear algebra. So, for example, the vector dot product is used to calculate the intensity on the light intensity on the surface of an object, and then different rendering methods exist that apply those different intensities on the surfaces. You can either render a surface or a surface in a single color. This is then called flat shading. You can do Gouraud shading. Then you define 3 intensities on the corners of a triangle, and you can linearly interpolate. And you can also do form shading. Then you don't interpolate simply the intensity, but you actually first interpolate the normals, and you have then to calculate the vector dot product for all the points, and that gives better results than Goro shading. And however, you have to watch out that you get the gamma exponent right, and you will also see it's quite easy to produce Mach bands. You even see them on screen here, that are those parts where you don't have an even intensity distribution, and which show up like bands. Really expensive on an older CPU is perspective correct texture mapping. You then have screen coordinates, and want to know for each of the screen coordinate what point in the texture is being is supposed to be displaced. I put for completeness, I put the formulas here you can use for that. So you also see that needs 2 divisions per single screen pixel, and that was really slow until pixel shaders could do it in hardware. You can actually map any quadrangle to any quadrangle, but you need to solve a linear equation system with 9 unknowns for this. This is also a preparation you then need to do. And you also need to normalize, because you have one free parameter. You could use the normalization equation that is shown in the last line. Yeah, and today it's totally easy. You have your GPU, you have vertex shaders, you have pixel shaders. And the really difficult parts are hidden away for the most time. So all the demonstration graphics in the slide were rendered using a VIC-20. I will show them live in a short shot after the slide has ended. I have already put most of the demonstration programs online in the VIC-20 denial forums. This is the link, you find the thread. And anyhow, thanks for your attention, and have fun at revision. Are there any questions? Yeah, they come completely with source. Of course, for the 6502, they are completely with source. And if there are also any questions afterwards, there is an extra discussion thread for this talk. The thread itself is being held like a workshop. So you are invited to ask questions there in the discussion thread, and if they are within reason, I can also take your ideas and take a look to incorporate them as the workshop expands further.
On VIC-20, or you have the time to check it on Atari 8-bit or other computers?
It's entirely possible to use all those routines also on other 8-bit computers. So mainly because the implementation is in 6502 machine language, they are of course geared to that kind of CPU. I actually would be interested how, for example, a Z80 coder would approach the geometry engine with the same setup of multiplications, but implemented in Z80 assembly code. Yeah?
Are there approximations?
Yeah.
Are there approximations to the perspective correct texture mapping that get close to the correct look in computer operations?
Yeah. Okay, that's actually at the moment I have not the implementation on the 6502 itself, but it is planned. What I did already was an implementation in pure meshing code on the ARM CPU, which uses 32-bit integer variables and which works. So I can just do a full perspective correct. The only thing that is about with rounding errors when the coordinates go, when the coefficients of that I showed you, A, B, C, D, E, they have to be calculated. They are about 16-bit numbers, and there are truncating errors. But in the whole, the pixel errors are on the order of less than half a pixel. And what I also did is an implementation in C, not actually for animations directly, but rather for perspective correcting photographs. So you can, for example, take a photograph of a painting in a museum and make, if you photograph it from a skewed angle, you can correct it and have the original once again. That works quite well, even if the camera has some perspective distortions. But actually, for this workshop, I've also planned to make an implementation of perspective projection also on the 6502. Yeah. So, thank you once again. We have a VIC-20 here in the hall, and just you see, I have lots of examples here. I just show you the bookends of that. So we have here the first example. And all the way possible to see it later on your real hardware. We are on, when you're coming into the hall, our group is sitting on the left side, roughly in the middle of the hall. And also for completeness, the other end, the hidden lines. Here. And, well, okay, I should also take, this is here the 3D world in a few seconds. And the computer takes a few seconds to think about this, and this is pure basic. Thank you. Enjoy the party.